In this fourth video on motion, we are going to delve deeper into solving mathematical and graphical problems involving motion. So you were assigned the following question for homework in the previous lesson, and it states, an object starts from rest, moves in a straight line with a constant acceleration, and covers a distance of 64 meters in 4 seconds. So we have an object, and I always like to draw a very quick sketch graph just to get a visual perspective of the problem. So we have an object and its initial velocity vi is 0 meters per second because it's at rest. It covers a distance of 64 meters in 4 seconds. So delta x is 64 meters, and in this case, because the vehicle is traveling, or the object is traveling in a straight line and it's not changing direction, its distance and its displacement or change in position is the same, 64 meters. However, with the displacement we associate a direction with it as well. We will come to that. It does not tell us what the final velocity is, so that's unknown, and it asks us to calculate its acceleration, and notice it's a constant acceleration. I also like to write down a data list, and as I've mentioned before, that it may seem unnecessary for simple problems like this, but when one starts to deal with two-body problems, it can be quite useful to do. So delta x is 64 meters. Let's define a sign convention like we did in dynamics. So let's define the direction of motion as positive and the opposite direction as negative. So delta x is going to be plus 64 meters. V initial is 0 meters per second. V final we do not know. The acceleration we do not know. We do know it's constant. And delta t is 4 seconds. So it asks us to calculate. It doesn't state that we must use the graph to do so. So we can use equations of motion. So writing down equations of motion, we start off with delta x equals v initial delta t plus a half a delta t squared. Substituting in, delta x is plus 64 meters. V initial is 0, so that first term is going to be 0. Plus half times the acceleration, which we don't know. Delta t squared is 4 seconds. Delta t is 4 seconds, so delta t squared is going to be 4 seconds squared. And so we've got 64 equals 4 squared is 16 times a half is 8, so it's 8a, and a is 64 divided by 8, which gives us 8. So this is 8 meters per second squared, and it's positive. So therefore we can say that acceleration, and because acceleration is a vector and it asks us to calculate its acceleration, because it's a vector, you have to assign a direction to the final answer. So this is 8 meters per second squared in the original direction of motion. We do not assign east or west to it because we have not been given the original direction in terms of east or west or north or south in the question. Now, you might be asking, so how did I know that this was the correct equation to use? Well, this is a very similar problem to the one we used in the previous video, but if you didn't have that fresh in your memory, a good thing to do is to take the equations of motion like I did in the previous video and tick what you have and put a little cross on what you don't have. And if you look at it in that way, you can see in this equation, the only unknown in this equation is the quantity that we're looking for, namely the acceleration. Therefore, we can use this equation of motion to solve for the unknown quantity that we're being asked for. Now that we've done this, and there is our answer, I would suggest that you put this answer back into your data table, and it's plus 8 meters per second squared. So this was question A. Now looking at question B, we are asked to determine the final velocity. Now the final velocity is to be found in two equations explicitly as the subject of the equations. So the first one is V final equals V initial plus A delta t, and the second one is V final squared equals V initial squared plus 2A delta x. Now if we check to see what we have and what we don't have, we don't have V final. We do have V initial. We do have the acceleration as we've now calculated it. We have delta t. We have V initial, we have A, and we have delta x. So in both these equations, we only have V final, that is the unknown. So we can use either of them. I'm going to choose to use the first one because it doesn't have a square in it. So I would not have to square root at the end of the calculation. But I encourage you to try this one as well and see that you get the same answer. So using the first one, we're going to substitute in. So V final is what we're looking for. And pertaining to the arrows, as soon as I have written the equation down, I no longer keep the arrows in the equation because it makes it a bit complicated. But the fact that I've put the arrow in there is making me sensitive to the fact that I need to be aware of directions when I work with the vector quantities in the equation. So V initial is 0. The acceleration is plus 8 meters per second squared. The time is 4 seconds. And this gives us a final velocity of 8 times 4 is 32 meters per second, positive. So V final is 32 meters per second in the original direction of motion. Now, let's just look at the way we assign marks. So there would be a mark assigned for the equation, a mark assigned for the substitution, a mark would be assigned for the magnitude, and then a mark would be assigned for the direction. So students often lose a mark in a problem like this because they do not explicitly put the direction in their answer. They leave the answer like that, which is not wrong numerically, but then they have to interpret that that plus sign is in actual fact a direction. And that's why I like to explicitly put the plus sign in there, because I'm keeping myself sensitive to the fact that this is a vector quantity and that plus sign has a meaning of the direction being in the original direction of motion according to our sign convention as defined at the beginning of this problem. Now, before I do C and D, I would like to draw or sketch the graphs for this particular system. It hasn't been asked in this particular question, but with the approach that I employ in teaching motion, there's value in us doing it, and then when we do C and D, we can refer back to the graphs to get a deeper understanding of what we've actually done. Now, when sketching the graphs of motion, I prefer to sketch them underneath each other in this way. The delta x, or the change in position versus time graph on the top, the velocity versus the time graph in the middle, the acceleration versus the time graph at the bottom. Now, there's a reason why I do this, and it will become clearly apparent by the time I'm finished with sketching these graphs. The data list is now complete. And for some of you who use other textbooks or may be having tutor lessons from someone outside of the school, you might have come across a different way of denoting or labeling the quantities that describe the motion of a system. Now, in some syllabuses or syllabi, for delta x they use S, and for V initial they use U, and for V final they use V, and for A acceleration they use A, and for delta t they use T. And there's nothing wrong with using this as long as one then adjusts the equations. And then the equations become the following: V equals U plus AT, V squared equals U squared plus 2AS, X equals UT plus a half AT squared, and X equals U plus V over 2 times T. This is known as the SUVAT system by some teachers. And there's nothing wrong with doing this. If you use the equations correctly in an exam, they will mark you correctly. But we're not going to employ this approach. We are going to use the symbols that fit the equations as they are found on the formula sheet in the NSC exams. So let's start with the easiest of the graphs, and that is the acceleration versus time graph. The acceleration is 8 meters per second squared, and it is a constant. Now, the time was 4 seconds, so we're going to, for these three graphs, we are going to cover a time period of 4 seconds. And there's value in being able to see these graphs under each other in order to strengthen and reinforce the relationship between them. The acceleration is plus 8 meters per second squared, so it's a positive value. We do not need to draw a scale because these are sketch graphs. We do need to put in the plus 8. And there is our acceleration versus time graph. Simple, it's a horizontal straight line. The next one is the velocity time graph. Now, we know that the initial velocity was 0 meters per second, and that the final velocity is 32 meters per second. This would be 32, and we need to indicate that because it is a significant value. And then with sketch graphs, we only need to draw the shape of the graph, which is a straight line, because this is uniform accelerated motion. So the velocity changes at the same rate every second, namely 8 meters per second per second. So now we have two of the graphs, but the most difficult graph is the position versus time graph. Now we know that its initial position was 0 meters by definition. That's where we started looking at the object. So we would put in the 0. I denote a point as a dot with a circle around it. You don't need to do that in sketch graphs, but I'm just doing it out of habit. The final change in position after 4 seconds is 64 meters. So we represent it up there, and that's going to be 64. But now we are faced with the question, what is the shape of the graph? Now, to take you back to the video before this, when we had acceleration that was greater than 0, then our position versus time graph looked like this. It was a increasing parabola where the curvature was positive. By that I mean that as you move along the parabola, the gradient or the slope of the tangent to the parabola continually increases. And the reason for that is that the velocity is increasing per second, so therefore the amount of displacement per second is increasing. When the acceleration was negative, then the change in position versus time graph had a negative curvature, looked like that. And the reason for that is that with a negative acceleration, where the object is moving in the positive direction, per second the velocity is decreasing, therefore the amount of change in position or displacement per time interval of 1 second is decreasing, and therefore we find that this is a negative curvature because the gradient or the slope of the tangent to the position versus time graph is getting less per second. Now looking here, we can see that our acceleration here is a true acceleration in the sense that it is a positive acceleration and not a negative acceleration, which would be a deceleration in this case. So we can now draw this graph with confidence, starting at 0 and then drawing a positive curvature parabola like that. But now I would like to draw your attention to a deeper relationship between these three graphs. And that is the following. If we take the gradient of this graph, we take the rise over run, then the gradient of the velocity versus time graph is the acceleration. We've learned this. And we can now go back and extend it to that at this point here, if we look at this point here, at the same time, if we take the gradient of the tangent to the position versus time graph, delta x over delta t, then that gives us the velocity, because the velocity is the change in position versus time. So the gradient of the position versus time graph gives us the velocity versus time graph if you work out the gradients over the full time interval, and the gradient of the velocity time graph gives us the acceleration versus time graph. We learned that when we worked with the area under a velocity time graph, then that area gave us the change in position at that particular time interval. So for high school purposes, we are going to stop here. When you go to university, when one has learned integral calculus, one will also explore how the velocity can be gained from the acceleration by working with the area of an acceleration versus time graph and using what we call an integral. So this is a very important set of graphs that one needs to keep in mind, because you're going to use these graphs or similar shaped graphs in the future. And you're going to see at the end of this video, I'm going to assign you a problem where you are going to have to deal with accelerated motion, constant velocity motion, and decelerating motion with a change in direction. And you're going to need to reproduce graphs very similar to this. So let's now stop here with graphs and let's move on to answering C and D. Now in C, we are asked to work out the time it would take for the object to cover half the distance. Now one's got to be very careful. You need to go back to your data table and you need to redo it. The initial velocity is still 0 meters per second. The acceleration is 8 meters per second squared. But the time now is what we are looking for. It's not the 4 seconds. And V final will be different. And delta x is not going to be 64 meters now, but it's going to be plus 32 meters, because we are now looking at how much time it will take to cover the half of the change in position, or half of the distance covered in 4 seconds. Now, one might jump to the immediate conclusion that half the distance is half the time, and so it should be 2 seconds, but you're going to see that it's not going to be 2 seconds, and we'll explain why just now. So using delta x equals v initial delta t plus a half a delta t squared. We're going to always write that down. Do not skip that step. And now substituting in, delta x is plus 32. V initial is 0. So that first term, this term is going to be 0, because 0 times the time is 0. And adding now a half times the acceleration plus 8 meters per second squared times delta t squared. So this is 32 equals a half times 8 is 4. So this is going to be 4 delta t squared. Divide 32 by 4, that gives us 8. So delta t is the square root of 8, which gives us 2,83 seconds. Now, this is more than half of the time, which was half of the time would have been half of 4 seconds is 2 seconds. So the question is, why does it not take half of the time? And the answer is that if one considers the fact that this is accelerated, and if we look at the graphs that we drew in the previous slide, then if this is 4 seconds and that's 2 seconds, so if we draw this halfway like that, then one can see that if we look at the velocity versus time graph, we know that the area under the velocity time graph gives us the change in position at that time value. Now we can clearly see this area is much bigger than this area, because in the second half of the motion, and half of the motion, I'm talking about the second 2-second time interval, because the velocity is higher, it is covering more distance or change in position per unit time. So in the second half of the motion, from a time perspective, it's going to cover much more distance or displacement. And therefore, in order to find what the time is for half of the distance, which is what we've done, so at 32 meters, we find that the time is longer because it takes longer to cover that distance, because initially the object is starting from 0 meters per second, and so it needs to be accelerated until it gets to a point where it's covered the 32 meters. The next 32 meters is covered very quickly because it's traveling at a higher velocity. So in D, we are now asked to work out the distance covered in half the time. So half the time would be half of 4 seconds, which is 2 seconds. So we don't know this change in position or this distance. Remember, I use change in position, distance and displacement as the same thing because there's no change in direction of the motion. So they're the same magnitude-wise. So now, using delta x equals v initial delta t plus a half a delta t squared, and now substituting in delta x equals v initial 0, so the first term is 0, plus a half times a is 8 plus 8, delta t is 2 seconds squared, so delta x equals a half times 8 is 4, times 2 squared is 4, 4 times 4 is plus 16 meters, and so delta x is 16 meters in the original direction of motion. Don't forget to put in the direction when you're being asked to calculate a vector quantity. Now, here too you can see that in half the time it doesn't cover half the distance. So let's go back to the graphs that we sketched earlier in this problem. So it's easier to see now because we've already looked at the two graphs in the context of half the distance in the previous problem. Now let's look at half the time. So half the time would be here, and we can clearly see that in half the time the change in position is not half of the total change in position, and that's because in the first 2 seconds the object is traveling at a much lower velocity than it is in the last 2 seconds. Therefore it covers less distance. If you look at the area there, is less than the area in the second 2 seconds. And so this is because we're dealing with accelerated motion. So now that we have done this problem in detail, we can now move on to the second homework problem, and we're going to move through this a lot quicker. So considering the last of the homework problems, we read a ball is thrown downwards. Now this is very important, thrown, because often they will say a ball is dropped. Now if it's dropped, it has an initial velocity of 0 meters per second. But when a ball is thrown, when it leaves the hand, then it has a velocity greater than 0 meters per second. And in this case, the velocity is 10 meters per second. And the balcony is 15 meters from the ground. So there's the balcony. And the gravitational acceleration is 10 meters per second squared. Now, we've learnt a lot about acceleration due to gravity when we did universal gravitation, and we have been using g as 9,8 since grade 8 and grade 9, and so this problem is rounding it off to 10 meters per second squared. If you're not given 10 meters per second squared, then by default you would use 9,8. So we have a situation where the ball is thrown downwards. Now we're going to assume that where the ball starts at 0 meters, that it is 15 meters from the ground, because no other distances are given, so we make that assumption. They ask us to find the time required for the ball to hit the ground. So they want to know what is delta t. So let's start off with our sign convention. The motion is all downwards, so let's define down as positive and up as negative. I like to suggest always define your positive direction as the direction of the initial motion, which in this case is down. So now we can fill up our data table. Delta x we know is 15 meters, so it's going to be plus 15 meters because the change in position is from there downwards, and down is positive. V initial we know is plus 10 meters per second because the initial velocity is downwards. The final velocity we do not know. We're going to be asked to calculate that in the second part of this problem. The acceleration is plus 10 meters per second squared because acceleration acts downwards, and delta t is what we are looking for. Using delta x equals v initial delta t plus a half a delta t squared. We always write the initial equation down. Delta x is plus 15. V initial is plus 10. Delta t we do not know. The acceleration we do know is plus 10 meters per second squared, and delta t squared we do not know. So this gives us 15 equals 10 delta t plus 5 delta t squared. If we divide by 5 all the way through, we get 3 equals 2 delta t plus delta t squared. But this is a quadratic equation. So if we rearrange it by pulling the 3 across, we get delta t squared plus 2 delta t minus 3 equals 0. Now you might be feeling uncomfortable and going, whoa, okay, I wasn't expecting this. But we do mathematics in order to be able to apply it in other contexts. So let's see if we can factorize this. So you'll see here I have used basic factorization to determine what the factors are of this quadratic expression, delta t squared plus 2 delta t minus 3. Delta t times delta t gives us delta t squared. 3 times minus 1 gives us minus 3. So we have that delta t plus 3 times delta t minus 1 gives us 0, and it's always good to check. Delta t times delta t is delta t squared. Delta t times minus 1 is minus delta t. 3 times delta t is plus 3 delta t. Added together gives us 2 delta t, and 3 times minus 1 is minus 3. Therefore, delta t equals minus 3, or delta t equals 1. Now, a quadratic equation often gives us two solutions, but we can clearly see in this problem that there is only one solution for the time required for the ball to hit the ground. So what do we do now? Well, we look at the physical meaning of the solutions. We have got delta t equals minus 3. Minus 3 what? Minus 3 seconds. Well, we can't have a negative time. So we know that that solution is not, whilst it's a mathematical solution, it's not a physically acceptable solution in this case. So this delta t equals plus 1 second is the correct solution. Now, what happens if we get a quadratic equation which we can't factorize as easy as this? well, then you use the quadratic formula that you've learnt about in mathematics in order to solve it. Let's now look at the second problem. The second problem asks us, calculate the velocity with which the ball hits the ground. Now, often learners say, oh, well, the answer is 0 because when it hits the ground it stops. No, this is not what we're asking. We are actually asking, what is the maximum velocity of the ball under the influence of gravity before it is stopped by the ground? There's a whole lot of physics you're going to learn about in grade 12 to do with the impulse of the ground on the ball, the net force over a time interval to stop the ball. That's not what we are going to focus on yet. So we are looking at the velocity, the maximum velocity of the ball just before the ground acts on it. So now, looking at what we have, we know that the time that it takes is 1 second. And we have the initial velocity, we have the change in position, we have the acceleration. So what is the final velocity? So we now look at the equations that explicitly have the final velocity in them. So this is B. And we have V final equals V initial plus A delta T. And we have V initial, A, and delta T. And so we can work out V final. So V final is going to be V initial, which is plus 10. The acceleration is plus 10. And the time is 1 second. So therefore V final equals 10 plus 10 times 1 is 10 is plus 20 meters per second. And so we can write this as V final is 20 meters per second down. We could also have used the other velocity equation, V final squared equals V initial squared plus 2A delta x. Substituting in, we find that V final squared equals V initial squared, which is plus 10 squared, 2 times A. A is 10. Delta x is 15 plus 15. Remember, it's plus and plus. So V final squared equals 100. 2 times 10 is 20 times 15 is 300. So V final squared equals 100 plus 300 is 400. Square rooting both sides, we find that V final is 20 meters per second. Plus 20 meters per second. And so we get the same answer, irrespective of which of these two equations we use. Now, every year I get asked the same question by learners when they are confronted with a problem like this, where they are confronted with a quadratic equation when they use this position time equation. And they ask me the following. They ask, is it possible to first work out the final velocity using this equation and using the delta x is 15, A is plus 10, and the initial velocity, which you're all given at the start of the problem, work out V final, and then substitute V final in here, together with V initial and the acceleration to work out delta t? And the answer is yes. There is nothing wrong with doing that. It is mathematically correct. So if you feel more comfortable in doing that, please do so. But just please make sure that you explicitly state what you are doing, and when you answer question B, that you refer to your actual calculation that you did in A in order to find delta t. Now, let's look at the graphs. So we're going to do the graphs very, very quickly. So the acceleration is plus 10 and we are working over a time of 1 second. So it's not very long. We're working over a time of 1 second. So we're going to put 1 second line through there. All right. So that's 1, 1, 1. The acceleration is plus 10. We can see there it's plus 10. So the acceleration is plus 10 meters per second squared, and it's constant. So it's plus 10. The velocity starts at 10 meters per second. So it starts, I'm going to open it up a bit. It starts at plus 10. And we worked out that it ends at 20 meters per second. So it's there. So this is 20 meters per second. And it is a straight line. And then going to the change in position versus time graph, we know that it starts at its initial position, which we define as 0 meters. There. And after 1 second, it is going to have traveled the full 15 meters. So the final change in position will be 15 meters plus 15 after 1 second. And because it is accelerated motion, the velocity is in the positive direction by definition, and the acceleration is in the same direction and is positive. Therefore, we have a parabola that has a positive curvature. And so here too, again, you see the same similar shaped graphs as what you saw previously. Would it have been possible to have done this problem if we had switched the sign convention around and defined up as positive and down as negative? Absolutely. The negative, or should I rather say the disadvantage of that, would have been that you would have had to deal with more negative signs in your calculations than by defining the sign convention in this way. So I sincerely hope that this video has helped you to gain a deeper understanding of how to apply equations of motion and graphs of motion in problems that you will encounter in tests and examinations.